2:34 in the afternoon, broad daylight, something screamed across the sky over 5 states. No vapor trail, nearly horizontal, and even the geophysicist who tracked it says he's not 100% sure what it was. That should bother you. Because the fireball surge that began in March was supposed to be over by now. The model said mid-April it winds down. Instead, it went global. Europe is now logging 100+ witness events. A new bolide exploded over the Pacific barely 24 hours later. The Artemis II crew counted 5 impact flashes on the moon in under an hour, from a seat no human being has ever sat in. Meanwhile, 3 asteroids are threading the gap between us and the moon, including one tonight. Something has changed in our solar system. Stay with me, because by the end of this you'll understand why nobody has an answer yet. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update as this story unfolds. Drop a comment with where you are tuning in from, what time it is there, and tell me this. The moon just got hit 5 to 6 times in a single hour. The surge has gone global, and the models that said this would be over by now were wrong. So what happens when whatever is feeding debris into our neighbourhood does not stop? Let me know your thoughts in the comments. Now, let's get into it. Part 1. This was supposed to be over. 2:34 in the afternoon, not 2:34 in the morning, when the sky's black and anything bright enough to catch your eye could be dismissed as a plane, a satellite, a trick of tired vision. 2:34 in the afternoon, broad daylight. The sun is up, the sky is blue, and somewhere over the eastern seaboard of the United States, something is screaming through the atmosphere so fast and so bright that people standing in parking lots, sitting in traffic, walking their dogs in suburban neighbourhoods across 5 states, from Virginia to New York, stop what they are doing and look up. It is April 7th, 2026, and what those people are watching is not supposed to be happening. Let me set the stage for you, because the context here matters more than you might think. For the past several weeks, since roughly mid-March, the skies over North America had been putting on a show. Fireball after fireball, bright streaks of light tearing across the night sky, some of them leaving long glowing vapor trails that hung in the atmosphere for minutes. The American Meteor Society, which is the primary clearinghouse for fireball reports in the United States and Canada, had been logging numbers that were, to put it plainly, not normal. Witness counts were spiking, event frequencies were climbing, and by early April the statistical picture had become so unusual that the data crossed what scientists call a 4.5 sigma threshold, a level of deviation from the expected baseline so extreme that the odds of it being a random fluctuation are astronomically small. We are going to come back to that number later because it deserves its own conversation. But for now, just understand this. The surge was real. It was confirmed, and by the first week of April most models were predicting that it would begin to taper off. The thinking was reasonable. Whatever debris Earth had been passing through, whether it was connected to the interstellar object 3I Atlas, or a known meteor shower, or some combination, the geometry of our orbit should have been carrying us out of the densest part of the stream. By mid-April, things were expected to calm down. They did not calm down. April 7th was supposed to be part of the decline. Instead, it became the single most anomalous event in the entire surge, and the reason it stands out is not just because it happened in broad daylight, although that alone would make it remarkable. Daylight fireballs are rare. For an object entering Earth's atmosphere to be visible against a sunlit sky, it has to be releasing an extraordinary amount of energy, enough to outshine the scattered light of the sun itself across a wide area. Most meteors, even bright ones, would be completely invisible under those conditions. This one was not. It was seen clearly. It was seen by a lot of people. 228 eyewitness reports were logged with the American Meteor Society within the first 48 hours. That is not a trivial number. That is the kind of reporting volume you get from a major nighttime event. Not something that happened while the sun was shining. But the strangeness does not stop at visibility. The trajectory of this object was wrong. Or rather, it was unusual in a way that made experienced observers pause. Most meteors enter the atmosphere at a steep angle. They come in high, they burn fast, and they either disintegrate entirely or punch through to the surface as meteorites on a relatively direct path. The April 7th fireball did not do that. It came in nearly horizontal. Witnesses described it moving laterally across the sky, not plunging downward. Analysts who reconstructed its path estimated that it travelled approximately 117 miles through the atmosphere at a speed of roughly 30,000 miles per hour. That is a long atmospheric transit, a very long one. And the angle of entry, that shallow, almost flat trajectory, is the kind of geometry that raises immediate questions because it changes everything about how the object interacts with the air around it. And then there is the detail that, for many observers, was the most unsettling of all. There was no vapor trail, nothing. No glowing line hanging in the sky behind it. No persistent ionization track. No slow-fading ribbon of superheated gas marking the path it had taken. The March fireballs, many of them, had produced spectacular trails. Long luminous streaks that lingered for minutes, sometimes visible from hundreds of miles away. That is normal behaviour for a meteor of significant size. The physics are straightforward. As the object ploughs through the atmosphere at tens of thousands of miles per hour, it compresses and superheats the air in front of it, ablating material from its surface, creating a column of ionized gas and vaporized rock that glows brightly and fades slowly. It is one of the most reliable signatures of a high-energy atmospheric entry. The April 7th object did not leave one. Instead, what witnesses reported was a tight, bright, concentrated point of light moving across the sky, almost like a spotlight being dragged across a ceiling. No spreading glow, no diffuse cloud, no trail, just the object itself, burning forward and then gone. Some witnesses reported flashes. Some reported sound, a dull boom or rumble that arrived minutes after the visual event, consistent with a sonic shockwave travelling from high altitude. That confirms energy release. That confirms this was a real, physical object moving at hypersonic speed through the atmosphere. But the absence of a trail tells you that something about this object, or something about the way it was moving, was fundamentally different from the events that came before it. Stefan Burns is a geophysicist who has been tracking the fireball surge closely since it began. He runs analysis on trajectory data, witness reports and sensor readings. He's been one of the most visible voices in the effort to understand what has been happening in our skies since March. And when the April 7th data came in, his response was not confident. It was not dismissive. It was not even particularly analytical, at least not publicly. What he said was this: he was not 100% sure what it was. Now that might sound like a throwaway comment, but I want you to sit with it for a moment. Because when someone who has been doing this work for months, who has analysed dozens of these events, who has access to the trajectory reconstructions and the sensor data and the eyewitness databases, when that person looks at an event and says they are not sure what they are looking at, that is not a casual remark. That is a signal. That is someone telling you as carefully as they can that the pattern they had been tracking just broke. And that is the central problem with April 7th. It does not fit. It does not fit the March events. It does not fit the expected decline. It does not fit the behavioural profile of known meteor showers. And it does not fit the trajectory models that had been used to explain the earlier surge. It is the largest fireball event of April so far, and it arrived at the exact moment the phenomenon was supposed to be ending. So the question is no longer whether the surge was real. That debate is over. The data settled it. The question now is something much more uncomfortable. What exactly are we looking at? Because the surge did not end. It did not taper off the way the models predicted. And the behaviour of the objects involved appears to be changing. Not just continuing, changing. The character of the events is shifting. The type of objects entering our atmosphere seems to be different from what we saw in March. The geometry is different. The physical signatures are different. And the geographic distribution, as we are about to see, has expanded dramatically. This is not a spike that is fading. This is starting to look like a phase shift, a transition from one state to another. And if that is what this is, then April 7th is not an outlier. It is the first clear signal of whatever comes next. If this was not the end, if the fireball surge did not wind down the way it was supposed to, then what exactly are we moving into? Part 2. Behavioural breakdown. Why experts paused. To understand why the April 7th event caused so much quiet alarm among the people who study these things professionally, you need to understand what they were expecting and how completely this object defied those expectations. Let me walk you through the comparison, because it matters. The March fireballs, the ones that kicked off this entire investigation, behaved in ways that were, for the most part, consistent with what we know about high-energy atmospheric entries. They were bright, they were dramatic. Many of them were large enough to produce sonic booms heard across wide areas, and critically they left trails. Long, luminous, slowly fading vapor trails that hung in the upper atmosphere like glowing scars. Those trails are not decorative, they're diagnostic. When a meteor enters the atmosphere at cosmic velocity, and we're talking about speeds that start at around 25,000 miles per hour and can exceed 160,000 miles per hour for the fastest objects, it does not simply fly through the air the way an airplane does. It collides with the air. The air in front of the object cannot move out of the way fast enough, so it gets compressed into a shock layer that reaches temperatures of tens of thousands of degrees. At those temperatures, the surface of the meteor begins to ablate, to melt, vaporize, and shed material. That ablated material, combined with the superheated air itself, forms the glowing column we see as a trail. The trail persists because the ionized gas takes time to cool and recombine. It is, in essence, a record of the object's passage, a thermodynamic receipt. The March events left long receipts, bright, dramatic, sometimes colourful, hanging in the sky for minutes. Classic meteor behaviour, textbook stuff. Now, look at April 7th, same general category of event, a large object entering Earth's atmosphere at high speed, releasing enough energy to be visible in broad daylight. But the signature was completely different. No trail, no lingering glow, no slow fading column of ionized gas marking the path. Just the object itself moving tight and bright across the sky, and then nothing. That absence tells a story, and it is a story that does not have a comfortable ending. There are only a few physical explanations for why a high-energy atmospheric entry would fail to produce a visible trail, and none of them are boring. The most straightforward possibility is composition. If the object was made of something unusually dense, something metallic, for example, like iron-nickel, its ablation behaviour would be very different from a rocky-orite object, and radically different from the fragile, porous material typical of cometary debris. Dense metallic objects lose mass more slowly. They do not shed a wide cloud of vaporized material the way a loosely bound rocky body does. They punch through the air more efficiently, concentrating their energy release into a tighter zone around the object itself, rather than spreading it out along the trail. The visual result would be exactly what witnesses described. A bright, compact point of light with no spreading wake. But composition alone does not fully explain the picture, because the entry angle adds another layer of complexity that is hard to untangle. The April 7th object came in nearly horizontal. That matters for trail visibility in ways that are not immediately obvious. A steep entry means the object is plunging through rapidly thickening layers of atmosphere, encountering denser and denser air as it descends. That rapid transition amplifies ablation. It is like dragging a piece of ice across a hot griddle. The faster you push it down, the more steam you get. A shallow entry, by contrast, means the object is skating along at roughly the same altitude for a much longer time, encountering air of relatively constant density. The ablation rate may be lower, even though the total path length is much longer. In theory, this could produce a fainter, more diffuse trail that might be invisible in daylight conditions, in theory. But the problem with that explanation is that we have seen shallow entry fireballs before, and they usually do still produce visible trails. Not always as dramatic as steep entry events, but visible. The total energy deposited over a 117-mile path at 30,000 miles per hour is enormous regardless of angle. Something should have been glowing behind this object. The fact that nothing was, or at least nothing that 228 observers could see in daylight, pushes the explanation beyond simple geometry. And then there is the terminal behaviour. This is where things get genuinely interesting, and where some of the more cautious analysts started choosing their words very carefully. Near the end of its visible path, the April 7th object appears to have split into two pieces. That by itself is normal. Fragmentation during atmospheric entry is one of the most common behaviours for meteors of significant size. The stresses involved, aerodynamic pressure, thermal shock, internal fractures, are enormous, and most natural objects are not structurally uniform enough to survive them intact. They break apart, sometimes into 2 or 3 large pieces, sometimes into hundreds of fragments that produce a spectacular cascade of light. The Chelyabinsk event in 2013, for example, involved catastrophic fragmentation that released the energy equivalent of roughly 500 kilotons of TNT and injured over 1,000 people from the resulting shockwave. The April 7th fragmentation was much smaller, 2 pieces, but it is the timing and the character of the breakup that caught attention. Some observers described a sequence that suggested the object decelerated before fragmenting, that it appeared to slow down and then came apart. Now, I want to be very careful here, because human perception of distant, fast-moving objects is unreliable. We are terrible at judging velocity changes in things we're seeing for the first time, especially at great distances, especially in daylight. So I am not going to tell you the object definitely slowed down. What I'm going to tell you is that the observational data was consistent enough with that interpretation to make some analysts uncomfortable, and inconsistent enough with standard expectations to make them want more data before committing to an explanation. Why would that matter? Because meteors do not decelerate significantly in the upper atmosphere under normal conditions. They lose speed gradually due to drag, yes, but the process is smooth and continuous, not abrupt. An apparent deceleration event before fragmentation would suggest either an unusual structural transition within the object, a sudden change in cross-sectional area due to partial breakup, for example, or an unusual density profile that changed how the object interacted with increasing atmospheric pressure. Either way, it would be telling us something about the physical nature of the object that does not fit standard assumptions. And here is where we need to step back and connect this to the bigger picture, because the behavioural differences between March and April are not just interesting scientific trivia. They are evidence of something that matters for the central question of this entire investigation. What is out there, and is it changing? If the March fireballs and the April 7th event were caused by the same debris source, the same stream of material, the same population of objects, then you would expect broadly similar behaviour. Similar compositions, similar entry signatures, similar trail characteristics. Variations, sure, because no 2 rocks in space are identical, but the general profile should be consistent. What we are seeing instead is a shift, a categorical difference. March gave us bright, steep, trail-leaving fireballs consistent with rocky or cometary debris. April 7th gave us something flat, dense, tight, and trailless. Those are not variations within a single population. Those are signatures of different populations, and that has enormous implications. Because it means the debris environment Earth is passing through may not be a single stream. It may be layered. Multiple populations of material from different sources, overlapping in time and space. Some of it could be cometary, some of it could be asteroidal, some of it could be material that has been floating in the inner solar system for millions of years, only recently perturbed into Earth-crossing orbits. The March events and the April events might not be the same phenomenon at all. They might be different chapters of the same larger story, written by different authors. Now, there are people who have gone further than this in their speculation. Some observers have floated ideas about controlled trajectories, about objects exhibiting behaviour that does not match any natural explanation. I want to acknowledge that those conversations exist, because pretending they do not would be dishonest. But I also want to be clear. There is no evidence in the current data that requires a non-natural explanation. What there is evidence for is something almost as unsettling: natural objects behaving in ways that the existing models did not predict, and that the existing categories do not comfortably accommodate. Burns's hesitation, his public statement that he was not 100% sure what the April 7th object was, is the most important data point in this part of the story. Not because it confirms any particular theory, but because of what it tells you about the state of expert confidence. Scientists who track meteors for a living do not usually say, "I don't know," in public. They hedge, they qualify, they offer probabilistic assessments. But they almost always have a working explanation they are willing to share. The fact that Burns did not for this event tells you that the pattern recognition he had been building since March, the framework that allowed him to contextualize each new fireball within a developing model, broke. April 7th did not fit the framework. It did not just extend the trend, it introduced a new variable, and when behavior changes, the natural next question is whether origin has changed too. Because if the April 7th object came from a different source than the March fireballs, that changes everything about what we think is happening, and everything about what we should expect to happen next. The orbit data, as it turns out, has something very specific to say about that, and what it says is not reassuring. Part 3. The orbit problem nobody's talking about. Every fireball leaves a signature, not just the visual streak across the sky, not just the possible sonic boom or the fragments that might survive to reach the ground, but a mathematical one, a trajectory, a line through space and time that, if you have enough data points, you can trace backward. And that backward trace is where the real story lives, because it tells you where the object came from, not just which direction it arrived from, but where it was before it arrived, what orbit it was on, what part of the solar system it had been travelling through, and with enough precision, what might have sent it on a path that ended with it screaming through Earth's atmosphere at 30,000 miles per hour on a Monday afternoon. The technique used for this kind of analysis is called Monte Carlo simulation, and the name makes it sound more exotic than it is. The basic idea is simple. You take the observational data, the trajectory angle, the speed, the position, the time, and you feed it into a physics model that simulates the motion of objects under gravity. Then you run that simulation backward, not once, but thousands of times, each time varying the input parameters slightly within the range of observational uncertainty. The result is not a single orbit. It is a cloud of possible orbits, a probability map showing where the object most likely came from. If most of those simulated trajectories converge on a similar region of space, you have a high confidence origin. If they scatter, you have a problem. For the April 7th fireball, the Monte Carlo results did converge. The simulated trajectories clustered toward the far side of the solar system, an origin consistent with an object that had been on a long elliptical orbit, swinging out beyond the asteroid belt and back in toward Earth's neighbourhood. That is already interesting, because it rules out a lot of the most common sources. This was not a piece of debris from a near-Earth asteroid on a tight orbit. This was something that had travelled a long way to get here. But here is where it gets genuinely significant, and this is the part that, as far as I can tell, is not getting the attention it deserves. Since the fireball surge began in March, one of the leading hypotheses for the source of the increased activity has been connected to an object designated 3I Atlas. This is the third confirmed interstellar object ever detected passing through our solar system, after Oumuamua in 2017 and Borisov in 2019. 3I Atlas was identified earlier this year, and its trajectory through the inner solar system put it in a position where debris associated with it, either material it was shedding or material it had gravitationally disturbed, could plausibly intersect Earth's orbit during the March-April timeframe. The idea was elegant. It explained the timing, it explained the sudden onset, and for the March fireballs, at least some of the trajectory data showed partial alignment with the 3I Atlas debris stream model. The April 7th fireball does not align. When you run the Monte Carlo simulations for this event and compare the resulting orbit cloud to the predicted trajectory of 3I Atlas associated debris, they do not match. The geometry is wrong, the approach direction is wrong, the velocity profile is wrong. Whatever the April 7th object was, and wherever it came from, it was almost certainly not part of the 3I Atlas debris stream. I want you to understand what that means, because it is the kind of finding that sounds technical, but has enormous implications. If the March surge was potentially linked to 3I Atlas, and the April 7th event is not, then we are no longer looking at a single source explanation. The neat, tidy story, interstellar object passes through, sheds debris, Earth flies through debris, fireballs happen, fireballs stop, that story just collapsed. We are now looking at a minimum of 2 independent sources contributing to the same period of elevated activity. And the moment you accept that, the entire framework for understanding the surge has to be rebuilt. Because think about what this means in practical terms. In March, you could argue that the fireballs were a transient phenomenon, Earth encountering a narrow ribbon of debris from a known object, passing through it over a few weeks, and then moving on. That is how meteor showers work. The Perseids come from Comet Swift-Tuttle, the Geminids come from asteroid Phaethon. You identify the source, you predict the timing, and you expect the show to end when the geometry changes. If 3I Atlas was the source, the surge had a built-in expiration date. But if April 7th came from somewhere else, from a completely different region of the solar system, on a completely different orbit, then the expiration date is gone. You cannot predict when something will stop if you do not know where it's coming from. And worse, you cannot rule out additional sources. If two independent debris populations are producing fireballs in the same time frame, there could be 3, or 5, or more. The coincidence of timing does not mean the sources are related. It might mean that something broader has changed, something that is sending more material from multiple directions into the inner solar system simultaneously, and that brings us to the asteroid belt. The asteroid belt sits between Mars and Jupiter, roughly 2 to 4 times the Earth-Sun distance from the centre of the solar system. It is not, despite what science fiction has trained you to imagine, a dense field of tumbling rocks that you would need to dodge if you flew a spaceship through it. It is mostly empty space. The total mass of all the asteroids in the belt combined is less than 4% of the mass of the Moon. But what the belt does contain is a vast population of objects on relatively stable orbits, objects that have been circling the Sun for billions of years, held in place by a complex balance of gravitational forces. That balance is dominated by Jupiter, whose enormous mass creates resonance zones within the belt, specific orbital distances where Jupiter's gravitational tug adds up over thousands of orbits, gradually nudging asteroids into new trajectories. Some of those new trajectories are stable, others are not, and some of them, over long timescales, send material inward, toward Mars, toward Earth, toward the inner solar system. This is not speculative. This is one of the primary mechanisms by which near-Earth asteroids are created. Material gets gravitationally shuffled out of the main belt and into orbits that cross the paths of the terrestrial planets. It has been happening for as long as the solar system has existed, but it happens at a relatively steady, predictable rate. The question that the April 7th orbit data raises is whether that rate has recently changed. Because if the April 7th object originated from the far side of the solar system, on a long elliptical orbit consistent with asteroid belt origin, and if it was not connected to 3I Atlas, then the most straightforward explanation is that it was a piece of main belt debris that was recently perturbed into an Earth-crossing orbit. And the word recently is doing a lot of work in that sentence because in orbital mechanics, recently can mean anywhere from months to thousands of years ago. But the fact that it is arriving now, during a period of anomalously high fireball activity, alongside other objects that appear to be coming from different directions, that timing is hard to ignore. Something may have changed in the gravitational dynamics of the asteroid belt. A shift in Jupiter's resonance zones, a collisional cascade where one asteroid impact produces fragments that then collide with other asteroids, producing more fragments in a chain reaction that sends debris scattering in all directions. Or something even less well understood, a slow, cumulative drift in orbital parameters that has been building for decades or centuries and is only now producing visible results. The honest answer is that nobody knows what caused the shift, not yet. What the orbit data tells us is that the shift appears to be real, that material is arriving from directions and on trajectories that do not fit a single explanation. The March events might be one thing, the April 7th event is likely another, and both are part of a larger pattern that is, as of right now, still expanding. Because while all of this analysis was happening, while scientists were arguing about orbits and compositions and entry angles, the fireball surge was not waiting for them to figure it out. It was spreading. Geographically, statistically, and in ways that made the "it's winding down" narrative look increasingly naive. If the source is not what we thought, if there is no single, neat origin point that explains everything, then something closer to home has changed. Something in the dynamics of our own solar system. And the evidence for that change was about to get a lot harder to dismiss. Part 4. Europe lights up, while the US slows. Here is a pattern that almost fooled everyone. In the last week of March and the first few days of April, the fireball reporting rate in North America appeared to dip slightly. Not dramatically, not enough to declare the surge over, but enough for the cautiously optimistic to start suggesting that maybe, just maybe, the peak had passed. The American Meteor Society's daily intake of new reports ticked down from the extraordinary highs of mid to late March. A few headlines floated the idea that things were returning to normal, and if you were only looking at the US data, you might have believed it. But the fireballs had not stopped. They had moved. Starting in early April, Europe began logging fireball events at rates that mirrored what North America had experienced weeks earlier. And not small, ambiguous events, large, high-confidence fireballs with massive witness counts. One event drew over 80 individual reports from observers spread across a wide geographic area. Another topped 100 witnesses. These are not marginal sightings. These are events visible across hundreds of miles, bright enough to trigger dozens of independent reports from people who had no idea anyone else was watching the same thing. Now, the first objection that any reasonable skeptic should raise, and it is a valid objection, is whether this could be a reporting artifact. Maybe Europeans simply became more aware of the phenomenon because of media coverage of the March surge in North America. Maybe the reporting infrastructure improved, or social media amplified awareness, or people who would previously have shrugged off a bright light in the sky started filing formal reports because they had read about fireballs in the news. This is a real concern in any observational science. When you tell people to look for something, they find more of it. That is human nature. But the data pushes back against that explanation in ways that matter. The European events were not borderline sightings that might have been missed under normal awareness levels. They were high-energy, multi-witness events of the kind that get reported regardless of media cycles. An 80-plus witness fireball is not the result of heightened awareness. It is the result of a large object producing a large amount of light over a populated area. People report those events whether they have heard about a fireball surge or not, because when the sky suddenly lights up and a streak of fire crosses the horizon, you notice. You do not need a news article to tell you that was unusual. More importantly, the timing and distribution of the European events tell a story that simple reporting bias cannot account for. If the phenomenon were the same set of predictable meteor shower activity that happens every year, the geographic progression would follow known patterns. You would expect activity to be concentrated during specific nights when Earth passes through well-mapped debris streams, with the radiant point of the shower favouring specific hemispheres at specific times. What actually happened does not match any known shower profile. The European events occurred during a period when no major meteor shower was active. They appeared in regions and at times that are not predicted by any standard model. And this brings us to something that the orbit data from Part 3 of the previous act already hinted at: the possibility that Earth is not passing through a narrow stream of debris, but through something more like a cloud, a diffuse, unevenly distributed region of material that does not behave like the neat, predictable ribbons left behind by known comets. If the debris environment is cloud-like rather than stream-like, then you would expect exactly what we are seeing: activity that shifts geographically over time as different parts of Earth's surface rotate into the densest portions of the cloud. North America gets hit first, then as Earth moves along its orbit and rotates on its axis, Europe begins to intercept a different cross-section of the same broad debris field. Think of it like driving through a rainstorm. If the rain is falling in a narrow band, like a squall line, you pass through it and you are done. But if the rain is spread across a huge area, unevenly, with pockets of heavy downpour and patches of lighter drizzle, then you are going to be getting wet for a long time, and the intensity will vary depending on exactly where you are at any given moment. The geographic shift from North America to Europe is what you would expect if the debris rain is broadly distributed rather than narrowly concentrated. And here is the critical point, the one that connects this geographic spread back to the central question driving this entire investigation. This behaviour is not what we would expect if the surge were fading. A phenomenon that is winding down does not expand its geographic footprint. A debris stream that Earth is leaving behind does not start producing major events on a different continent. The geographic expansion is evidence that the debris environment is persistent and widespread, that Earth did not pass through a patch of it and come out the other side, but rather that we are embedded in something larger than the initial models assumed. The surge did not fade, it spread, and that changes the calculus on everything that comes next. Part 5. The 4.5 Sigma Reality Check. Let me talk about numbers for a moment, because numbers are the one thing that does not care about interpretation. The American Meteor Society maintains one of the most comprehensive fireball databases in the world. Every report that comes in, from casual observers, from dedicated sky watchers, from people who just happen to be pointing their security camera at the right part of the sky, gets logged, time-stamped, geolocated and cross-referenced against other reports to identify confirmed events. Over years and decades, this produces a baseline, an average rate of fireball activity that reflects the normal background flux of material entering Earth's atmosphere. That baseline includes seasonal variations, known meteor showers, random sporadic activity, all of it averaged out into a statistical picture of what normal looks like. In 2026, from mid-March through early April, that baseline shattered. The deviation from the expected average crossed the 4.5 sigma threshold. Now, if you are not someone who thinks about statistics on a daily basis, that number might not mean much to you, so let me translate it into something more intuitive. Sigma is a measure of standard deviation, how far a data point sits from the average. 1 sigma is a mild fluctuation. 2 sigma is unusual. 3 sigma is what most scientists consider the threshold for "this probably isn't random." In particle physics, 5 sigma is the gold standard for declaring a discovery. It is the level of confidence that was required to confirm the existence of the Higgs boson. 4.5 sigma is sitting between "this probably isn't random" and "this is almost certainly real." The probability of a 4.5 sigma deviation occurring by chance, assuming normal distribution, is roughly 1 in 300,000. To put that in context, if you flipped a coin and got heads 18 times in a row, you would be at similar odds. It could happen. But you would not bet your life on it being a coincidence. The witness report averages did not just tick upward, they jumped. The number of reported events per day during the peak of the surge was multiple times higher than the long-term average for the same period. And the character of those events reinforced the statistical picture. This was not a case of more people reporting the same number of fireballs, it was more fireballs, period. The average brightness was higher, the average witness count per event was higher, and critically, the percentage of events that produce sonic booms, audible shock waves generated when an object is large enough and fast enough to create a sustained pressure wave that reaches the ground, hit 79% for the largest events in the surge period. That last number deserves a moment of your attention. 79%. Under normal conditions, the vast majority of fireballs are too small, too high, or too slow to produce audible sound at ground level. A sonic boom from a meteor means that a substantial object, not a grain of sand, not a pebble, but something with real mass, survived deep enough into the atmosphere to create a shock front that propagated all the way to the surface. When nearly 4 out of 5 major events are doing that, you're not looking at a normal background fluctuation. You're looking at a population of larger than average objects entering the atmosphere in a cluster. 11 major events were logged in a span of roughly 20 days. 11. To understand why that number matters, you need to know what major event means in this context. It means a fireball bright enough, widely enough witnessed, and energetic enough to be flagged as a significant entry rather than a routine meteor. Under normal conditions, you might expect 1 or 2 events of that caliber in a 20-day window. 11 is not a minor uptick. 11 is a different category entirely. And here is where the skepticism about reporting bias, the idea that maybe people are just filing more reports because they heard about fireballs on social media, runs into a wall it cannot climb over. Sonic booms are not subject to reporting bias. You cannot convince yourself you heard a boom because you read a news article. Either the air shook or it did not. Either your windows rattled or they did not. The sonic boom data is physical, not perceptual. It is confirmed by infrasound stations, by seismic sensors, by security camera audio. It is, for all practical purposes, immune to the suggestion that this is just a perception effect. The same goes for the fireball brightness data. The American Meteor Society uses standardized magnitude estimates that are cross-referenced across multiple independent witnesses. A single observer might misjudge brightness. 200 observers spread across multiple states are going to converge on a reliable estimate. When those estimates consistently indicate events brighter than the long-term average, the explanation is not people are paying more attention. The explanation is the objects are bigger. And this multi-platform convergence is what elevates the surge from interesting anomaly to genuine environmental signal. It is not just the AMS data. NASA's Center for Near-Earth Object Studies has independent sensors. Infrasound networks operated by the Comprehensive Nuclear Test Ban Treaty Organization detect atmospheric explosions. Weather radar has picked up debris from some of the larger events. When multiple independent detection systems using completely different physical principles all converge on the same conclusion, More objects, bigger objects, more energy. The probability of a mundane explanation drops to near zero. At this level of statistical confidence, with this degree of multi-platform confirmation, coincidence stops being a serious explanation. Something is putting more material into Earth's path, and that something has been doing it consistently for weeks, across continents, with no sign of stopping. The data is not ambiguous, the data is screaming, and the data was about to get louder. Because less than 24 hours after the April 7th fireball confused analysts with its trailless horizontal flight across 5 states, something else entered the picture. Something detected not by eyewitnesses or meteor cameras, but by the space-facing sensors that watch for explosions in Earth's atmosphere from orbit. Part 6. The event that happened 24 hours later. On April 8th, less than a day after the anomalous daylight fireball over the eastern United States, NASA's Center for Near-Earth Object Studies, known by its acronym CNEOS, logged a bolide detonation over the central Pacific Ocean. The energy release was estimated at approximately 0.1 kilotons, that is roughly 1/10 the explosive yield of the smallest nuclear weapon ever tested. In absolute terms, it is a modest amount of energy, certainly not a civilization-threatening event. But in the context of what had been happening for the previous 3 weeks, the timing was impossible to ignore. A bolide, for those unfamiliar with the terminology, is a specific category of fireball, one that terminates in a bright flash, indicating a catastrophic fragmentation or explosion in the atmosphere. Not all fireballs are bolides. Most meteors simply fade as they lose mass through ablation. A bolide is the exception, an object that holds together until the aerodynamic stresses exceed its structural integrity, at which point it explodes. The CNEOS detection system is designed to pick up exactly these kinds of events, using a network of sensors originally built to monitor for nuclear detonations. When CNEOS logs a bolide, it means the energy release was significant enough to register on systems designed to detect weapons tests. The April 8th event occurred over open ocean, far from any populated area, which means there were no eyewitness reports. Nobody saw it. Nobody heard it. It was detected purely by instrumentation, a reminder that the events we do see, the ones that produce 200 witness reports and make the evening news, represent only a fraction of what is actually entering our atmosphere. CNEOS monitoring has known blind spots. It misses smaller events, it has gaps in geographic coverage, and it cannot detect objects that burn up at high altitude without producing a sharp terminal flash. The actual rate of atmospheric entry during this period is almost certainly higher than the instrumented record shows. What the April 8th bolide confirms is continuity. It confirms that the elevated rate of material entering Earth's atmosphere did not pause after April 7th. It did not take a day off. Barely a full rotation of the planet later, another significant object arrived. One anomalous event can be explained away. 2, back to back, in the middle of a statistical surge that is already at 4.5 sigma, cannot. And the Pacific bolide is a reminder of something uncomfortable. We're only seeing the events that happen over land during clear weather, within range of populated areas and monitoring stations. The Pacific is vast, most of it is empty of human observers. If objects of this caliber are detonating over open ocean with this frequency, the total flux of material is significantly higher than the count we are tracking. The debris environment is not calming down, it is not pausing. It is continuing at a rate that, by every available measure, exceeds what the models predicted and what the historical baselines define as normal. And while all of this was happening in Earth's atmosphere, while analysts were chasing trajectory data and statisticians were computing sigma values, something was also happening 240,000 miles away. Something that, for the first time in human history, we were actually able to watch from the perfect vantage point, and what it showed makes the Earth-based data look like a footnote. Part 7. The Artemis II observation window. While fireballs were lighting up skies on 2 continents and bolides were detonating over the Pacific, 4 astronauts were doing something no human beings had ever done before. They were behind the moon watching the sun disappear. Artemis II launched as the first crewed lunar mission since Apollo 17 in 1972, more than 50 years of absence from that part of space. Think about that for a second. More than half a century since any human being had been out there, beyond low Earth orbit in the actual neighbourhood of the moon. Generations of scientists built entire careers studying the lunar environment, from 250,000 miles away, using telescopes and robotic probes and orbital sensors, because that was all we had. And then, in April of 2026, 4 people climbed into a capsule, strapped themselves to a rocket and went there. Its trajectory carried the crew on a free return loop around the Moon, a path that briefly placed them on the far side of the lunar body relative to Earth. And during that passage, something happened that the mission timeline had predicted, but that no one had ever witnessed from that perspective: a solar eclipse. Not the kind you see from Earth, where the Moon passes between you and the Sun. This was the reverse. The crew watched Earth pass between the Moon and the Sun, casting a shadow, dimming the light, and creating a 57-minute window of reduced solar glare during which the lunar surface became unusually easy to observe. 57 minutes. That is not a long time. It is barely enough to cook a frozen pizza. But in those 57 minutes, the Artemis II crew, Commander Reed Wiseman, Mission Specialist Christina Kos, and their crewmates observed something that sent a quiet ripple through the planetary science community. Something that, in the context of everything we have been discussing, transforms this story from a terrestrial anomaly into something much larger. They saw the Moon getting hit 5 to 6 times in 1 hour, impact flashes. Brief, bright bursts of light on the lunar surface, each one marking the moment a small object, a meteoroid, a piece of debris, a chunk of something, struck the Moon at cosmic velocity. No atmosphere to slow it down. No ablation, no fireball, no sonic boom, just impact. Kinetic energy converted instantly to light and heat, as the object and a small portion of the lunar surface vaporized on contact. Each flash lasted a fraction of a second, a pinpoint of brilliance against the grey, ancient surface, and then it was gone, leaving behind a fresh crater that no human eye would ever see individually, but that, collectively, over billions of years, had given the Moon the battered face we all recognize when we look up at night. The crew's reaction was palpable. Wiseman and Co. both described the observation with obvious excitement, the kind of restrained but genuine amazement that comes from seeing something you know is scientifically significant in real time. These are not people who are easily impressed. They are astronauts. They have trained for years. They have simulated every phase of this mission hundreds of times. But there is a difference between knowing, intellectually, that the Moon gets hit by debris, and watching it happen through your window while you float in a spacecraft 240,000 miles from home. They were not watching a simulation. They were not reviewing data after the fact. They were counting impacts as they happened, in real time, from a vantage point that no human being in the history of our species had ever occupied, and the number they counted was higher than anyone expected. Now, why does this matter for the story we have been telling? Why should you care that a few astronauts saw some flashes on the Moon? It matters because the Moon is an independent witness, and in any investigation, scientific or otherwise, an independent witness changes everything. Everything we have discussed so far, the fireballs, the witness reports, the sigma values, the sonic booms, the CNEOS bolide detections, all of it comes from Earth. All of it is filtered through our atmosphere, our detection systems, our reporting infrastructure, our observational biases. Every single data point in the fireball surge has been collected by instruments sitting at the bottom of a 100-kilometre thick ocean of air, operated by a species that is prone to excitement, pattern recognition, and media-driven attention cycles. A reasonable skeptic could still, at this point in the story, construct an argument that the apparent surge is partly or fully an artifact of Earth-based observation. Maybe our atmosphere is behaving differently, some change in upper atmospheric density or composition that makes meteors glow brighter or persist longer. Maybe solar activity is affecting how meteors present visually, increased ionization in the upper atmosphere amplifying the optical signature. Maybe the reporting systems are capturing a higher percentage of normal activity due to technological improvements or social media awareness. These are not strong arguments. The multi-platform data makes them very difficult to sustain, but they are conceivable. A determined skeptic could hold that line. The Moon eliminates all of them, every single one. The Moon has no atmosphere. There is no ablation effect to misinterpret. There are no weather conditions to complicate observation. There is no social media driving awareness, no reporting infrastructure to improve, no heightened public anxiety skewing the numbers upward. The Moon is just a rock, a big, airless, ancient rock that has been sitting in space for 4.5 billion years, getting hit by things. When something hits the moon, it either produces a visible flash or it does not. There is no ambiguity. There is no interpretation required. There is no bias to account for. It is the cleanest possible dataset you could ask for in a situation like this. And the observation conditions during the Artemis II eclipse window were about as good as they could possibly be. The solar eclipse reduced glare on the lunar surface, making faint flashes easier to see. The crew had direct visual access through the spacecraft windows, human eyes, adaptive, sensitive, and capable of detecting brief events that an automated camera might miss or misclassify. And the eclipse itself provided a defined observation window, a known start time and end time, which allows for precise rate calculations. You know exactly how long they were watching, and you know exactly how many flashes they saw. That is the kind of controlled observation that scientists dream about. 5 to 6 impacts in 57 minutes, observed by human eyes, from a vantage point that no one has ever occupied before, during a window of optimal observing conditions that will not repeat itself on the next mission. Let me connect this back to the central thread of this investigation, because it is easy to get swept up in the spectacle of astronauts watching the moon get pelted and lose sight of what it means for the bigger picture. If the debris environment around Earth is elevated, if more material is orbiting in our neighbourhood than usual, then the moon should be getting hit more often too. This is not a leap of logic, it is basic geometry. The moon is right there. It orbits at roughly the same distance from the sun as Earth. It sweeps through approximately the same region of the solar system. It shares our cosmic neighbourhood. Any broad increase in the flux of small objects in the Earth-Moon system should affect both bodies, not one or the other, both. If Earth is getting hit more, the moon should be getting hit more. If the moon is getting hit more, Earth should be getting hit more. They are two targets sitting in the same shooting gallery, and that is exactly what the Artemis II observation suggests. Not hints at, not weakly implies, suggests, with the kind of straightforward, unambiguous clarity that makes the skeptic's job very, very difficult. The same debris environment that is producing anomalous fireballs in our atmosphere is also striking the moon, in real time, observed by humans, confirmed from outside Earth's sphere of observational bias. This is not a model prediction, this is not a statistical inference, this is 4 people looking out a window and counting flashes. The fireballs were telling us one story. The moon just told us the same story from a completely different angle, literally and figuratively. And when 2 independent datasets measured by completely different methods in completely different environments, with completely different biases and limitations, converge on the same conclusion, you are no longer in the territory of anomaly. You're no longer debating whether the signal is real. You're in the territory of confirmation. The signal is real. The debris environment has changed. And it has changed not just for Earth, not just for our atmosphere and our sky watchers and our sensor networks, but for the entire Earth-Moon system. But the confirmation gets stronger, because those 5 to 6 impact flashes per hour do not just confirm that the moon is getting hit, they confirm that it is getting hit at a rate that, under normal conditions, should not be happening. And the gap between what should be happening and what is happening, that gap is where the real story lives. Part 8. Why that number should not happen. Let me give you a baseline, because without one, 5 to 6 impacts per hour is just a number. And numbers without context are just noise. So let me give you the context that turns this noise into a signal you cannot ignore. Lunar impact monitoring is not new. Multiple programs around the world have been watching the moon for impact flashes for years, decades in some cases. NASA's Meteoroid Environment Office runs one of the most systematic monitoring efforts, using ground-based telescopes to observe the night side of the moon, the dark portion visible from Earth, and record brief flashes of light that indicate meteoroid strikes. The technique is straightforward in principle. You point a sensitive camera at the unlit part of the moon, you wait, and when something hits the surface hard enough and fast enough to produce a burst of light, you record it. Similar programs operate in Europe and Japan, each contributing data to a growing global picture of how often the moon takes a hit. Over time, across thousands of hours of cumulative observation, these programs have produced a fairly reliable picture of the lunar impact rate, how often objects large enough to produce a visible flash actually strike the surface. The normal rate, outside of known meteor showers, is less than 1 visible impact per hour, and I want you to sit with that number for a moment, because it is going to become very important. Less than 1 per hour. That is an average that includes a lot of natural variation. Some hours produce nothing at all, some produce 1 or 2, and the overall average, smoothed across many observation sessions over many years, sits below 1. It is a quiet background hum. The moon gets hit constantly by microscopic particles, of course, dust grain-sized objects that produce no visible flash and leave craters too small to see from Earth. But objects large enough to generate a flash you can detect from 250,000 miles away are relatively rare. Less than 1 per hour on average during quiet periods. Now, that average goes up during major meteor showers, when Earth, and by extension the Moon, passes through a known debris stream left behind by a comet or asteroid. The flux of incoming material increases, and so does the lunar impact rate. During the peak of the 2014 Geminids, for example, monitoring programs recorded elevated impact rates that corresponded neatly to the enhanced flux of meteoric material from the shower's parent body, the asteroid Phaethon. The Perseids produce similar spikes each August. These are well understood, well predicted events. The shower starts, the impact rate goes up. The shower ends, the rate comes back down. Clean, predictable, explained. But early April 2026 does not correspond to any major meteor shower. I cannot stress this enough. There is no known shower active during this period at the levels that would explain what the Artemis II crew observed. The Lyrids, which are the nearest significant shower in the calendar, do not typically peak until late April, and even at their peak, they are a moderate shower. Pleasant to watch from a dark field, sure, but not the kind of event that produces dramatic spikes in lunar impact frequency. In early April, the meteor shower calendar is essentially quiet. The background is the background, and the background says less than 1 visible impact per hour. The Artemis II crew observed 5 to 6. 5 to 6 visible impacts in 57 minutes works out to a rate of roughly 5 to 6 per hour. At minimum, that is 5 times the normal background rate. 5 times. During a period with no active meteor shower that would explain it. No known debris stream. No predicted enhancement. Just the quiet, ordinary early April sky, which apparently is no longer quiet or ordinary. And here is the part that should really give you pause. What the crew saw represents only the tip of the iceberg. Visible lunar impacts have a detection threshold. Think of it like an iceberg. You see the part above the water, but most of the mass is hidden below the surface. For a lunar impact to be visible from 240,000 miles away, the impacting object has to be large enough and moving fast enough to produce a flash bright enough to cross that enormous distance and register in a human eye or a camera sensor. We are talking about objects at least a few centimeters across, hitting at speeds of tens of kilometers per second. Anything smaller produces a flash too faint to see at that range. It still hits. It still makes a crater. It still deposits energy. But you would never know it happened from where the Artemis II crew was sitting. The 5 to 6 observed flashes, therefore, represent only the upper end of the size distribution, only the biggest, most energetic impacts out of a much larger total population. For every flash the crew saw, there were almost certainly dozens, maybe hundreds, of smaller impacts happening simultaneously that fell below the visibility threshold. The actual total impact rate, including all the objects too small to produce detectable flashes, is almost certainly much, much higher than 5 to 6 per hour. We are seeing the elephants, we are not seeing the mice. And if there are 5 times more elephants than usual, the number of mice is probably elevated by at least the same factor, if not more. There is also a geographic dimension to the Artemis II observation that adds another layer of information, and it is a layer that points directly back to the central question of this investigation. The impact flashes were not concentrated in one area of the lunar surface. They were not clustered on one hemisphere or bunched along one latitude band. They were distributed across a wide range of locations, including regions near the lunar equator and near the South Pole. That geographic spread is telling you something important about the source of the impacting material. Here is why. If the impacts were coming from a single, narrow debris stream, like a meteor shower, you would expect them to cluster. The Moon would be facing into the stream from a specific direction, and the impacts would preferentially strike the leading hemisphere. The side of the Moon pointed toward the incoming material. You would see a pattern, a concentration of flashes on one side, a relative absence on the other. That is exactly what happens during known meteor showers, and it is one of the ways lunar impact monitors confirm that an observed spike corresponds to a particular shower. The Artemis II observations showed no such pattern. The impacts were scattered, equator, south pole, different longitudes, different latitudes. That kind of wide geographic distribution is not consistent with a narrow directional stream. It is consistent with something much more diffuse, a broadly distributed population of debris coming from multiple directions at once, which is exactly, and I mean exactly, the kind of cloud-like debris environment that the Earth-based geographic data was already suggesting. Remember how the fireball surge shifted from North America to Europe in a pattern that did not match any known meteor shower? Remember how the trajectory analysis showed objects arriving from different orbital origins? The lunar impact geography is telling the same story from a completely independent vantage point, and that convergence is the key. The statistical anomaly on Earth, the 4.5 sigma fireball surge, and the lunar impact rate anomaly are independent measurements of the same underlying phenomenon. They are two different instruments reading the same signal, two different witnesses testifying to the same event. If you saw elevated fireball activity on Earth and normal impact rates on the Moon, you might argue that something Earth-specific was going on, an atmospheric effect, a detection improvement, a media-driven reporting surge. If you saw elevated lunar impacts and normal fireball rates on Earth, you might argue that it was a fluke observation and a typically active hour, a calibration error in the crew's counting. But when both datasets spike simultaneously, during the same time period, in the same region of the solar system, with no known meteor shower to explain either one, the probability of coincidence drops to functionally zero. You're no longer looking for excuses, you're looking at confirmation. We're not looking at an Earth problem, we're looking at a solar system problem. The debris environment in the Earth-Moon neighbourhood has changed, and it has changed in a way that affects both bodies simultaneously. Whatever is sending more material into our atmosphere, whatever is producing the anomalous fireballs, the statistical surge, the behavioural shifts, is also sending more material into the Moon's face. The source is not local to Earth. It is not atmospheric. It is not an artifact of how we observe or how we report. It is out there, in the space around us and around the Moon, occupying the volume of the cislunar environment, and it is depositing material onto every surface it encounters at a rate that exceeds the normal background by a significant and measurable margin. The Artemis II crew did not set out to confirm the fireball surge. That was not on their checklist. They were on a trajectory test, checking systems and procedures for future lunar missions, validating the hardware that will eventually carry humans back to the lunar surface. The eclipse observation window was a bonus, a scientifically interesting opportunity built into a mission designed primarily for engineering validation. But what they ended up confirming, almost by accident, from a vantage point no human being had ever occupied, is that the anomaly is real. It extends beyond Earth's atmosphere. It is affecting the entire cislunar environment, and it is not something we can explain away by pointing at our own observational limitations, which brings us to the third layer of evidence, the one that is happening right now, in real time, and that you can verify for yourself if you know where to look. Part 9. The cislunar environment is crowded. While fireballs were entering Earth's atmosphere and impact flashes were lighting up the Moon, something else was happening in the space between them. And unlike the fireballs, which you needed to be in the right place at the right time to see, and unlike the lunar impacts, which required 4 astronauts in a spacecraft no human had ever occupied before, this third layer of evidence is the kind you can look up yourself right now on publicly available databases maintained by NASA. Asteroids were passing closer to Earth than they normally do, and they were doing it in clusters. In the span of roughly 2 weeks in late March and early April 2026, 3 separate asteroids made sublunar passes, meaning they flew between Earth and the Moon, closer to us than our own natural satellite. Not near the Moon, between the Moon and us, inside the perimeter. The objects were designated 2026 FM3, 2026 GD, and 2013 GM3. Their closest approach distances were 0.62 lunar distances, 0.65 lunar distances, and 0.68 lunar distances respectively. Let me translate that into something more tangible, because 0.62 lunar distances is the kind of phrase that slides right past you if you do not stop and think about what it actually means. 1 lunar distance, 1 LD is the average distance from the centre of Earth to the centre of the Moon, about 238,900 miles. That is the yardstick. That is the fence line of our immediate neighbourhood. Everything inside 1 lunar distance is, cosmically speaking, right next to us. 0.62 lunar distances is roughly 148,000 miles. To put that in perspective, that is a little more than halfway between Earth and the Moon. If you imagine the Earth-Moon system as a house, these asteroids were not passing by on the sidewalk, they were walking through the living room. Now, to be clear, none of these objects posed any impact threat. They were all relatively small, likely in the range of a few meters to a few tens of meters across, and their trajectories were well determined. They were going to miss us, and they did miss us. This is not a story about a near miss or a close call or any of the breathless asteroid headed for Earth headlines that pop up every few months and turn out to be nothing. This is a story about frequency, about how many objects are making these close passes and whether that number has changed. Under normal circumstances, sublunar asteroid passes happen, but not frequently. The typical rate, based on the catalogue of known near-Earth objects and their predicted flyby schedules, is roughly 1 every 12 to 18 days. That is the baseline. 1 object inside the Moon's orbit every 2 to 2.5 weeks. It happens, it gets logged, it makes the news for about 15 minutes, and everyone moves on. 3 in approximately 2 weeks represents a clustering that is above the average frequency. Not wildly above, this is not a 10 sigma event in the way the fireball surge is, but noticeably elevated, about twice the expected rate, compressed into a tight window, and elevated in a way that aligns with the broader pattern we have been documenting across every other dataset in this investigation. The timing alone is suggestive. 3 sublunar passes during the exact period when fireballs are spiking to 4.5 sigma above baseline, and the Moon is getting hit at 5 to 6 times the normal rate. That is either a coincidence, or it is a third manifestation of the same underlying phenomenon. And by this point in the story, I think you can guess where the weight of the evidence is leaning. Now, the immediate counter-argument, and it is a partially valid one, so I want to give it the respect it deserves, is detection bias. Our ability to find small asteroids has improved dramatically in recent years, and that improvement is accelerating. Better telescopes with wider fields of view, better survey strategies that cover more of the sky more frequently, better data processing algorithms that can identify moving objects against the background stars with higher sensitivity and fewer false positives. Programs like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera Rubin Observatory have pushed the detection threshold lower and lower, meaning we are now routinely finding objects that would have sailed past unnoticed 10 or 20 years ago. It is entirely possible, even probable, that some of the sublunar passes being logged today would have gone completely undetected in the early 2000s. We are seeing more close approaches in part because we are looking harder and looking better. That is a real factor, and it would be intellectually dishonest to wave it away. But here is the thing about detection bias, and this is critical. It has a boundary. Detection bias explains why we are finding more asteroids. It does not explain why those asteroids are there. Detection bias is an observational effect. It changes what we see, not what exists. And in this investigation, detection bias has exactly 0 explanatory power for the other 2 layers of evidence. Detection bias does not explain the fireballs. You cannot discover a fireball by looking harder. Either a large object enters the atmosphere and produces a brilliant streak of light visible across 5 states, or it does not. Either 228 people file eyewitness reports with the American Meteor Society, or they do not. Either the event produces a sonic boom that rattles windows and registers on infrasound stations, or it does not. Fireballs are not subtle. They are not lurking at the edge of detectability, waiting for a better telescope to reveal them. They announce themselves. The 4.5 sigma surge in fireball activity is not an artifact of improved detection. It is an artifact of more objects entering the atmosphere. Detection bias does not explain the lunar impacts. You cannot discover an impact flash on the Moon through improved detection technology when the observation was made by human eyes from a spacecraft. The Artemis II crew was not using some revolutionary new instrument. They were looking out a window. Their detection method was the oldest one in the scientific toolkit. A person watching and counting. The 5 to 6 impact flashes they observed in 57 minutes were bright enough to see with the unaided eye from 240,000 miles away. That is not a detection threshold that has recently improved. That is a detection threshold that has been available to any human being with functioning vision for the entire history of our species. We just never had anyone in the right place to use it before, so the asteroid clustering does not have to carry the weight of this argument on its own. It does not need to be a standalone ironclad proof that the debris environment has changed. It simply has to be consistent with the picture that the fireballs and the lunar impacts have already painted. And it is. Perfectly consistent. 3 sub-lunar passes in 2 weeks, during a period when the atmosphere is logging anomalous fireball rates, and the moon is taking hits at 5 times the background rate. The asteroids are not proving the case. They are corroborating it. They are the third witness walking into the courtroom and telling the same story the first 2 witnesses already told. What we now have is a 3-layer signal. 3 independent datasets collected by 3 different methods, in 3 different environments, subject to 3 different sets of biases and limitations, and all 3 are pointing in the same direction. Layer 1, the atmosphere, fireball rates elevated to 4.5 sigma above baseline, confirmed by the American Meteor Society. Sonic boom rates at 79% for major events. 11 significant fireballs in 20 days. Behavioral changes, entry angles, trail characteristics, composition signatures, suggesting multiple debris populations rather than a single source. Geographic spread from North America to Europe, a continuation and possible escalation of activity beyond the predicted decline window. Layer 2, the lunar surface. Impact rates 5 to 6 times the expected background, observed directly by the Artemis II crew during a 57-minute eclipse window. No active meteor shower to explain the elevation. Geographic distribution of impacts spread across equatorial and polar regions, consistent with a diffuse debris population rather than a directional stream, independent of all Earth-based observational biases, confirmed by human eyes from cislunar space. Layer 3, cislunar space itself. 3 sublunar asteroid passes in approximately 2 weeks, against a baseline expectation of roughly 1 every 12 to 18 days. Partially subject to detection bias, yes, but occurring during a time frame when 2 independent bias-resistant datasets are already showing anomalous elevation. Each of these layers, taken in isolation, could be argued away. A determined skeptic could construct a plausible alternative for any one of them. The fireballs could be reporting bias, more people looking up because of media coverage, filing reports they would normally skip. Sure. The lunar impacts could be a lucky observation during an atypically active hour. The crew happened to be watching during a random spike that is not representative of the broader rate. Unlikely, but conceivable. The asteroid clustering could be entirely an artifact of detection improvement. We are just better at finding small objects now, and the actual population has not changed. Defensible to a point. But when all 3 layers show the same signal, simultaneously during the same weeks, the arguments for dismissal start requiring more assumptions than the arguments for reality. You have to assume that the fireball surge is a reporting artifact, and that the lunar impacts were a statistical fluke, and that the asteroid clustering is purely a detection effect. Each of those assumptions is individually possible. Their simultaneous truth is not impossible, but it is improbable in a way that strains the word coincidence past its breaking point. At some point, and I would argue we have reached that point, the simplest explanation is the one that takes the data at face value. There is more material in the Earth-Moon neighbourhood than there was before, more rocks hitting our atmosphere, more rocks hitting the Moon, more rocks flying through the space between us. The debris environment has changed, not in a theoretical, model-dependent, arguable way, in a measured, multi-platform, independently confirmed way. And if you accept that, if you look at the atmospheric data, the lunar data, and the cislunar data, and you accept that all 3 are telling you the same thing from 3 different angles, then the final question is the most important one of all. It is the question that every data point in this investigation has been building toward. The question that the fireballs raise, the lunar impacts underscore, and the asteroid clustering punctuates. What changed? What is the mechanism? What is the process? What happened out there in the solar system we thought we understood that put more material on a collision course with Earth and the Moon at the same time? Was it a single event, a collision, a gravitational disturbance? Or is it something more gradual, something that has been building for years or decades and is only now crossing the threshold of visibility. Is it temporary? Is it cyclical? Is it going to fade? Or is it going to intensify? And perhaps most unsettling of all, is it going to get better or worse? Part 10. The Asteroid Belt Bulge Hypothesis. So here we are. The evidence is stacked 3 layers high. Fireballs in the atmosphere, impacts on the moon, asteroids buzzing through cislunar space, all elevated, all simultaneous, all defying the "it's winding down" narrative that was supposed to close this chapter weeks ago. The question that every data point, every trajectory analysis, every statistical anomaly has been building toward is the obvious one, the one you have probably been asking since the beginning of this investigation. Why? What is causing this? What changed? Stefan Burns, the geophysicist who has been tracking this surge since its inception, the same analyst who looked at the April 7th fireball data and said he was not 100% sure what he was looking at, has a working model. It is not a confirmed explanation. He would be the first to tell you that, and I want to be equally upfront about it. This is not a solved mystery. This is a best fit framework, a hypothesis that accounts for more of the observed data than any competing explanation, while still leaving critical questions unanswered. But it is worth understanding in detail because it illuminates both what we think we know and, perhaps more importantly, how much we do not. The model starts with a simple idea. Earth is currently passing through a region of the inner solar system that contains a higher than normal density of small debris. Not a narrow stream, like a meteor shower, where the debris follows a well-defined orbital path inherited from a parent comet. Not a single cluster of fragments from one breakup event, like the debris field left behind when a satellite gets destroyed. Something broader and more diffuse. A region where the background population of small objects is temporarily elevated across a wide volume of space, producing a sustained increase in encounter rates for anything passing through it. Earth, the moon, everything in our neighbourhood. The proposed source of this enhanced debris region is the asteroid belt. Now, before you tune out because you think you already know what the asteroid belt is, let me give you the version that actually matters for this story, because the cartoon version, the one you have seen in every science fiction movie, with spaceships dodging tumbling boulders in a dense field of rocks, is not just wrong. It is misleading in a way that will prevent you from understanding what Burns is actually proposing. So forget that image. Replace it with this one. The asteroid belt is a torus-shaped region of space between Mars and Jupiter, roughly 2 to 4 times the distance from the Earth to the Sun, that contains millions of objects ranging in size from dust grains to the dwarf planet Ceres, which is about 600 miles across. But here is the critical part. Those objects are not evenly distributed. They are not a uniform cloud. They are organised by gravity, specifically by the gravitational influence of Jupiter, which is so massive that it sculpts the internal structure of the belt the way a river sculpts a canyon over millennia. Jupiter does not just sit there being big. It reaches into the belt with invisible gravitational fingers and rearranges everything. Jupiter creates what are called resonance zones within the belt, specific orbital distances where an asteroid's orbital period has a simple, mathematical ratio to Jupiter's own. If an asteroid orbits the Sun exactly 3 times for every 1 time Jupiter completes an orbit, that asteroid is in what is called a 3-to-1 resonance. What that means, physically, is that every 3rd orbit the asteroid and Jupiter are in the same relative position, and the asteroid receives a gravitational tug from Jupiter at the same point in its trajectory. 1 tug is nothing. 100 tugs are nothing. But over thousands of orbits, over millions of years, those tugs add up. They accumulate, and they can do one of 2 things. They can stabilize an orbit, locking the asteroid into a predictable long-term path that keeps it safely in the belt indefinitely. Or they can destabilize it, gradually stretching the orbit from a near circle into an elongated ellipse, pulling it further and further from its original path until it becomes eccentric enough to cross the orbits of the inner planets, Mars first, then Earth. The famous Kirkwood gaps in the asteroid belt, regions at specific orbital distances that are conspicuously empty of asteroids, visible as clear lanes in plots of asteroid distribution, are the scars of destabilizing resonances. They are empty because every asteroid that once orbited there has been flung elsewhere by Jupiter's accumulated gravitational influence. Some were thrown outward, beyond the belt entirely. Others were thrown inward, toward the inner solar system. toward us. This is the primary mechanism by which the inner solar system gets its supply of near-Earth objects. It is not dramatic, it is not sudden, it is slow, it is continuous, and under normal conditions it is predictable. The rate at which new objects get injected from the belt into Earth-crossing orbits is roughly constant over timescales of thousands of years, a steady drip of material migrating inward, occasionally producing the fireballs and meteorite falls that have been part of Earth's experience for as long as it has existed. We know this rate is relatively stable because the population of known near-Earth objects has been consistent in surveys conducted over the past several decades. The supply line from the belt is open, but it flows at a roughly constant rate. Burns's hypothesis suggests that something disrupted this equilibrium, that the steady drip has temporarily become a surge. The concept he's been working with involves what you might call a bulge in the debris distribution, a localized region within or near the asteroid belt where the density of small objects is temporarily higher than the surrounding area. Think of it like a traffic jam on a highway. The overall flow of cars is constant, but at one specific stretch something has caused a pile-up, a higher than normal concentration of vehicles in a compressed space. If you are standing on an overpass above that stretch, you see more cars per minute than you would anywhere else on the road. The total number of cars in the system has not changed, but the local density has spiked. If Earth's orbit carried it through the inner edge of this bulge, the region where perturbed debris from the belt spills into the inner solar system after being ejected from resonance zones, you would see exactly what we are seeing: a sustained multi-week increase in fireball rates, lunar impact rates, and near-Earth object encounters. Not a one-day spike, not a single dramatic event, a persistent elevation across weeks, across continents, across multiple detection methods, a background hum that got louder and has not gotten quieter. The question, of course, is what created the bulge, and here the model offers several candidate mechanisms, none of which are mutually exclusive, meaning any combination of them could be contributing simultaneously. The first candidate is a shift in Jupiter's resonance structure. Jupiter is not a static gravitational influence. Its orbit is very slightly perturbed by the other giant planets, particularly Saturn. The gravitational dance between Jupiter and Saturn is one of the most important dynamical relationships in the solar system, and it produces slow, cyclical variations in Jupiter's orbital parameters over timescales of centuries to millennia. Those variations in turn cause subtle shifts in the locations and strengths of the resonance zones within the asteroid belt. A shift of even a fraction of a percent in a resonance boundary could destabilize a population of asteroids that had been stable for millions of years, objects that were sitting just inside the safe zone, orbiting peacefully, suddenly finding themselves just outside it, subject to the accumulated tugs that would gradually stretch their orbits and send them inward. This process would be invisible to us in real time. The shift would have happened centuries or millennia ago, but the debris, travelling on slow elliptical orbits, would only now be arriving in the inner solar system. We would be seeing the consequences of a cause that is ancient by human standards. The second candidate mechanism is a collisional cascade. Asteroids in the belt occasionally collide with each other. The belt is mostly empty space, yes, but over millions of years collisions happen, and a single collision between two large objects, each a few hundred meters across or larger, can produce thousands of fragments, ranging from boulder-sized chunks to gravel to dust. Those fragments inherit some of the orbital energy of their parent bodies, but they also get velocity kicks from the impact itself, scattering them in different directions. Some end up on orbits that remain in the belt, others end up on orbits that cross the inner solar system. If a significant collision occurred in the belt within the past few years or decades, the resulting debris cloud could still be spreading outward, with fragments gradually migrating inward under the influence of gravitational perturbations and the slow, steady push of the Yarkovsky effect. The collisional cascade model has an appealing feature. It naturally explains the mix of different debris types, rocky, metallic, possibly even ice-bearing, that the behavioral data seems to be suggesting. A single collision between two compositionally different asteroids would produce fragments of varying density and composition, exactly the kind of diverse population that could explain why the March fireballs and the April 7th event looked so different from each other. The third candidate is longer-term orbital diffusion driven by the Yarkovsky effect itself. This is the tiny but persistent thrust produced when an asteroid absorbs sunlight on one side, and re-radiates it as thermal infrared radiation. The photons carry momentum, and the recoil, infinitesimally small for any single photon, adds up over millions of years into a measurable force that slowly changes an asteroid's orbit. The direction of the change depends on the asteroid's rotation. Prograde rotators drift outward, retrograde rotators drift inward, but the net effect, over long time scales, is to gradually move objects from stable regions of the belt toward the edges of resonance zones. If a large population of objects happen to reach critical resonance thresholds at roughly the same time, a kind of gravitational rush hour, where decades or centuries of slow drift finally deliver a cluster of objects to the destabilization boundary simultaneously, you could see a pulse of inward migration that would elevate the debris flux in the inner solar system for months or even years. Each of these mechanisms has strengths and limitations that prevent any one of them from being a complete answer. The resonance shift model explains the timing and the persistence of the surge, but it is hard to verify without detailed observations of the belt itself, observations that current telescope surveys are not optimized to provide. The collisional cascade model explains the mix of different debris types and the broad geographic distribution of events, but it requires a collision event that has not yet been directly observed. We would need to find the crater, or the debris field, or some other signature of the impact, and in a belt containing millions of objects spread across billions of cubic miles of space, that is a needle in a haystack problem of the highest order. The orbital diffusion model explains the gradual onset of the phenomenon and is consistent with known physics, but it struggles with the relatively sudden spike in activity. If the process is gradual, why did the surge appear to start so abruptly in March? Burns' position, as I understand it, is that the bulge hypothesis is the best available framework, the one that accounts for the largest fraction of the observed data with the fewest ad hoc assumptions. It fits the pattern. It explains the geographic spread of fireballs from North America to Europe. It explains the statistical anomaly. It explains the behavioral diversity of the objects entering the atmosphere. It explains the multi-domain conformation from atmosphere, moon and cislunar space. It is, in the language of science, the most parsimonious explanation currently available. But it does not answer the most important question, the question that sits at the centre of this entire investigation like a locked door with no visible key. What triggered the shift? Something caused more debris to be injected into Earth-crossing orbits. Something changed the orbital dynamics of the region between Mars and Jupiter in a way that is producing measurable effects in the Earth-Moon system right now, today, this week. The model describes the pattern with reasonable fidelity. It does not identify the cause, and that gap between what we can see happening and why it is happening is the central unresolved tension of this entire story. It is the question that keeps the scientists up at night, the question that makes the models feel incomplete, and the question that, until it is answered, leaves open the possibility that the surge is not ending, because if you do not know what started something, you cannot predict when it will stop. This explains the pattern, but it does not explain the cause, and that distinction might be the most important one in this entire investigation. Part 11. The 3I Atlas complication. And then there is the question of 3I Atlas, the interstellar visitor. The wildcard that entered this story early seemed like it might explain everything, and then, just when we needed it most, stopped fitting the data. Let me take you back to the beginning, because the arc of this particular thread matters for understanding where we are now. When the fireball surge first became statistically undeniable in mid-March, one of the earliest and most compelling hypotheses centered on an object that, under different circumstances, would have been the biggest science story of the decade all by itself. 3I Atlas is the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua, discovered in 2017, that strange, elongated object that tumbled through the inner solar system, generated more theories than data, and left before we could get a good look at it. The second was Borisov, spotted in 2019, a comet clearly outgassing, behaving more or less the way cometary physics predicted an interstellar comet should behave. And then came 3I Atlas, identified earlier this year, on a hyperbolic trajectory that confirmed it originated from outside the solar system entirely, not born here, just passing through. The logic connecting 3I Atlas to the fireball surge was straightforward, and at the time it was elegant. an interstellar object passing through the inner solar system could interact with the local debris environment in two ways. First, it could shed material directly, come-tree outgassing, surface fragmentation, or the release of loosely bound dust and particles as it heated up during its approach to the Sun. That shed material, if it happened to intersect Earth's orbital path, could produce a temporary increase in the flux of small objects entering our atmosphere. Second, and more subtly, its gravitational influence could disturb existing debris, nudging objects that were already in near-Earth orbits into slightly different trajectories, potentially increasing the rate at which they encountered our planet. The timing worked. 3I Atlas's passage through the inner solar system coincided with the onset of the fireball surge in a way that felt too neat to be accidental. The geometry partially worked, at least for some of the early March events. Trajectory reconstructions for a few of the first fireballs showed approach directions that were broadly consistent with the region of sky where 3I Atlas debris might be expected. And the novelty of the explanation added a layer of significance that was hard to resist. Only the third known interstellar object in human history, arriving at a moment of heightened fireball activity. That is the kind of coincidence that feels like a clue. For a few weeks in March, 3I Atlas was the leading candidate, the working theory, the explanation that most of the analysts tracking the surge were cautiously building their models around. It was clean, it was testable, it had a built-in expiration date. Once Earth moved past the intersection point with the predicted debris stream, the surge would fade, the activity would return to baseline, and the story would be over. A fascinating but transient event, caused by a once-in-a-generation interstellar visitor, neatly explained and neatly concluded. But as we discussed in Act 1, the April 7th fireball broke that explanation. Broke it cleanly, broke it definitively, and broke it in a way that forced every model built around 3I Atlas back to the drawing board. When you run the Monte Carlo trajectory simulations for the April 7th event, tracing its path backward through the atmosphere, through near-Earth space, back out into the solar system to find its most probable origin, the result does not align with 3I Atlas. The approach direction is wrong. The velocity profile does not match. The orbital geometry points to a completely different region of the solar system than where 3I Atlas debris would be expected. Whatever delivered that daylight fireball to the skies over the eastern United States on April 7th, it was not material shed by the interstellar visitor. It was not part of the 3I Atlas debris stream. It came from somewhere else entirely, and that mismatch, combined with the orbit data for other recent events that also failed to align with the interstellar debris model, has forced a reassessment of 3I Atlas's role in this story. It has not been eliminated entirely. Some of the early March events may still be connected to its debris stream, but it can no longer serve as the single, unifying explanation for the entire surge. The neat, clean narrative collapsed, and what replaced it is something messier, more complicated, and in many ways more troubling. The current thinking, and I want to be crystal clear that this is speculative, not established, not peer-reviewed, not confirmed, is that 3I Atlas may have played an indirect role, not as a direct debris source delivering material to Earth's doorstep, but as a gravitational perturbation, a trigger that did not cause the debris directly, but may have set existing debris in motion. Here is how that would work, in principle. An interstellar object passing through the solar system does not just fly through empty space in a vacuum of influence. It carries mass, and mass means gravity. Every object in the universe with mass exerts a gravitational pull on every other object, and 3I Atlas, despite being small by astronomical standards, is no exception. As it moved through the inner solar system, it exerted a gravitational influence on everything it passed near. Every asteroid, every fragment, every grain of dust within its sphere of influence experienced a tiny tug as the interstellar visitor went by. Now, that tug is tiny, truly, vanishingly small. Interstellar objects, as far as we can tell, are not massive. Oumuamua was estimated to be perhaps a few hundred meters across. Borisov was larger, but still modest by solar system standards. 3I Atlas is in a similar size range. The gravitational influence of an object that small falls off with the square of the distance, meaning it drops to essentially nothing within a few tens of thousands of miles. You would not notice it. I would not notice it. A large asteroid would not notice it. But, and this is the critical but, The solar system is a place where millions of small objects exist in states of marginal stability. Objects sitting near the edges of resonance zones in the asteroid belt. Objects on orbits that are almost, but not quite, Earth-crossing. Objects that have been slowly drifting for millennia under the Yarkovsky effect, inching closer and closer to a gravitational tipping point. For these objects, the perturbation does not need to be large. It just needs to be present. It just needs to be the final straw. Imagine a hillside covered in loose rocks after a long dry spell. Most of them are stable, held in place by friction and the slight depressions they have worn into the soil over years of sitting in the same spot. They are not going anywhere. But some of them, maybe 5%, maybe 1%, are barely balanced, sitting at the very top of their little perch, held in place by the thinnest margin of friction, needing only the slightest push to start rolling. A human being walking across that hillside might not dislodge any rocks directly. Their footsteps are too light. Their weight is too small relative to the mass of the boulders. But the vibrations they create transmitted through the ground, spreading outward from each footfall, could be enough to free the ones that were already on the verge of moving. The ones that had been waiting, essentially, for any disturbance at all. The rocks that fall are not caused by the person in any direct mechanical sense. If you asked a physicist to calculate the force the person's footsteps exerted on a specific boulder, the number would be laughably small compared to the gravitational and frictional forces holding that boulder in place. And yet, without the person's passage, those specific rocks would have stayed put for another 1,000 years. The vibrations were not the cause. They were the catalyst, the last input in a system that was already primed to shift. 3i Atlas might be the person walking across the hillside. The debris reaching Earth right now might be the rocks that were already barely balanced. The interstellar object did not bring this material with it from another star system. It did not carry a cloud of debris through interstellar space and dump it in our neighbourhood. What it may have done, and I stress may, because this is hypothesis, not conclusion, is destabilise material that was already here. Material that was already orbiting in the asteroid belt, already sitting at the edges of resonance zones, already one small perturbation away from being sent spiralling inward toward Earth-crossing orbits. The interstellar visitor passed through, its gravity sent a whisper through the belt, and objects that had been stable for millions of years started moving. If that model is correct, the implications are significant but bounded. The perturbation was a one-time event. 3i Atlas passed through and kept going, heading back out into interstellar space, never to return. The debris it destabilized would represent a finite population, however many objects were sitting at the marginal stability threshold at the time of its passage. The surge would be real but temporary, fading as that finite population of newly destabilized objects either impacts Earth, impacts the Moon, falls into the Sun, or settles into new stable orbits. Under this model, we are seeing a pulse, not a permanent change. But this is where I have to pump the brakes, because the model is speculative in ways that matter. There is no confirmed mechanism by which 3i Atlas specifically perturbed specific asteroids into specific orbits. The gravitational math is plausible in a general sense. The physics of gravitational perturbation are well understood, but the specific application to this specific object and this specific debris population has not been verified. Nobody has identified a particular asteroid that was destabilized by 3i Atlas's passage. Nobody has traced a specific fireball back to an object that was sitting in a resonance zone before 2026 and is now on an Earth-crossing orbit because the interstellar visitor nudged it. The connection is inferred, not demonstrated. And the entire idea rests on a foundational assumption that is reasonable but unproven, that a population of barely stable objects existed in the right place, at the right time, in sufficient numbers to produce the observed surge when perturbed. If that population did not exist, if the objects near the resonance boundaries were more stable than the model assumes, or fewer in number, then 3i Atlas could have passed through without any measurable effect at all, and the real cause of the surge lies elsewhere entirely. What 3i Atlas represents, in the context of this story, is something more important than a confirmed explanation. It represents the limit of our understanding, the boundary between what we can measure and what we can explain. We can see the effects, the fireballs, the lunar impacts, the asteroid clustering. We can quantify the anomaly, 4.5 sigma, 5 times the baseline, 3 sublunar passes in 2 weeks. We can build models that describe the pattern with reasonable fidelity, the asteroid belt bulge, the debris cloud, the multi-source hypothesis. But the trigger, the thing that actually started this, the first domino in the chain, remains unidentified. 3I Atlas is a possible contributing factor. It is not a proven cause. And that distinction matters enormously, because the future depends on which is true. If 3I Atlas caused the surge through a one-time gravitational perturbation, the activity will eventually fade as the destabilized debris is used up. But if the real cause is something else, a collisional cascade that is still producing fragments, a resonance shift that is ongoing, a process we have not even identified yet, then the future trajectory of this phenomenon could be very different. It could persist, it could intensify, it could be the beginning of a longer-term shift in the debris environment of the inner solar system. The cause remains unresolved, the evidence of the shift does not. And that is the uncomfortable place this investigation has brought us, knowing that something has changed, being able to prove that it has changed, and not yet being able to say why. Part 12. 3 interpretations and none fully work. We have reached the part of this story where I'm supposed to tell you what is happening and what it means, and I'm going to do that as honestly as I can by laying out the 3 interpretations that the available evidence supports and telling you why none of them is entirely satisfying. Interpretation 1 is the coincidence stack. Under this reading, everything we have been discussing is a collection of independent anomalies that happen to be occurring at the same time. The fireball surge is one thing, maybe a statistical tail event, the kind of deviation that is rare but not impossible in a system with inherent randomness. The lunar impact rate is another thing, maybe the Artemis II crew happened to observe during an atypically active hour. The asteroid clustering is a third thing, partly real, partly amplified by improved detection. None of these phenomena are causally connected. They are simply co-occurring, and the human brain, which is wired to find patterns, is constructing a narrative out of noise. This interpretation has the virtue of requiring no new physics, no unknown mechanisms, no dramatic changes in the solar system. It asks you to accept only that unlikely things sometimes happen, and that when several unlikely things happen at once, it feels more meaningful than it is. Statistically, this is not a terrible argument. Strange coincidences occur. Lightning does strike the same spot twice. A 4.5 sigma event is rare, but rare things happen. The problem with interpretation 1 is cumulative. Each individual anomaly, taken alone, is unlikely but not impossible. But the probability of all of them occurring simultaneously and independently is the product of their individual probabilities, and that product gets very small very fast. When you multiply unlikely by unlikely by unlikely, you do not get, well, it could happen. You get, something else is going on. The coincidence stack is technically possible, but it requires more faith in randomness than the data seems to warrant. Interpretation 2 is the single underlying cause. This is the asteroid belt bulge hypothesis we discussed, the idea that a gravitational perturbation, a collisional cascade, or some other mechanism has injected an elevated population of debris into the inner solar system, producing all of the observed effects simultaneously. The fireballs, the lunar impacts, the asteroid clustering, all of them are different manifestations of the same environmental change. One cause, many symptoms. This interpretation is the strongest of the 3 in terms of explanatory power. It accounts for the multi-domain nature of the evidence. It explains why the effects are simultaneous. It is consistent with known physics and known mechanisms of debris migration. And it aligns with the trajectory data showing objects arriving from multiple directions. If the debris source is a broad region of the belt rather than a single point, you would expect a diversity of approach angles and orbits. The problem with interpretation 2 is the trigger. The model describes what is happening but not why. What caused the perturbation? When did it happen? Is it a one-time event or an ongoing process? Without answers to those questions, the model is incomplete. It tells you the room is on fire but not what started the fire. And the practical implications depend entirely on the answers. A one-time collisional cascade that happened 5 years ago would produce a pulse of debris that fades over months. An ongoing resonance shift could produce elevated activity for decades or centuries. The model cannot distinguish between these scenarios with current data. Interpretation 3 is the transitional environment, This is the broadest and most unsettling reading of the evidence. Under this interpretation, the solar system, or at least Earth's neighbourhood within it, is entering a period of enhanced debris activity that may persist for a long time, not because of a single event or perturbation, but because of cyclical or long-term processes that operate on timescales beyond human experience. There are mechanisms that could produce such a transition. The solar system oscillates slowly through the plane of the Milky Way galaxy as it orbits the galactic centre, and those oscillations can carry us through regions of higher or lower interstellar dust and debris density on timescales of tens of millions of years. Closer to home, the solar cycle, the roughly 11-year oscillation in the Sun's magnetic activity, is currently near a peak, and solar activity can influence the small body population indirectly by affecting the Yarkovsky effect, modifying radiation pressure on small objects, and even slightly perturbing the orbits of very small particles through electromagnetic interactions with the solar wind. The transitional environment interpretation does not require a single dramatic trigger. It suggests instead that multiple subtle factors may be converging: a solar maximum, a slow orbital diffusion process reaching critical mass, perhaps even the gravitational influence of 3I Atlas on top of pre-existing instabilities, to produce a period of enhanced activity that looks sudden from a human perspective, but is actually the cumulative result of processes that have been building for years or centuries. The problem with interpretation 3 is that it is difficult to test. If the transition is gradual and multi-causal, there is no single observation that would confirm or rule it out. You would need sustained monitoring over months or years, comparing ongoing rates to the baseline, looking for gradual decline or persistent elevation. It is the least falsifiable of the three interpretations, which makes it both the most intriguing and the most scientifically frustrating. And here is the uncomfortable truth that sits underneath all three interpretations. The April 7th fireball remains the most anomalous and least explained event in the entire sequence. Its trailless, horizontal, daylight trajectory does not fit comfortably into any of these frameworks. Interpretation 1 would call it a freak event. Interpretation 2 would call it evidence of a dense metallic debris component in the elevated population. Interpretation 3 would call it a signal of a changing character in the debris environment. None of these explanations is wrong. None of them is satisfying. What we are left with is a situation that science handles honestly but uncomfortably. A measurable phenomenon without a complete explanation. We can see it. We can quantify it. We can confirm it across multiple independent datasets in multiple independent environments. We can build models that describe the pattern, but we cannot yet explain what caused it. We cannot predict how long it will last, and we cannot rule out that it will intensify. The future scenarios branch from here in ways that depend on which interpretation is correct. If it is a coincidence stack, the anomaly resolves on its own, as each independent fluctuation returns to baseline. If it is a single perturbation, the debris pulse fades over weeks or months as Earth moves through and beyond the elevated region. If it is a transitional environment, this may be the new normal, or at least the new normal for the foreseeable future, and the data does not yet tell us which branch we are on. Let me bring this back to where we started, because the journey has been long and the landscape of evidence is wide, and it is easy to lose the thread. On April 7th, 2026, at 2:34 in the afternoon, a daylight fireball screamed horizontally across the skies of 5 eastern US states. It left no trail. It exhibited behaviour that the experts tracking it could not confidently explain. It arrived at the moment the fireball surge was supposed to be ending, and instead it marked the beginning of something new. Since then, the surge has gone global. Europe is logging events at rates that mirror North America's peak. A bolide detonated over the Pacific barely 24 hours later. The Artemis II crew watched the moon get hit 5 to 6 times in a single hour from a vantage point no human has ever occupied before. 3 asteroids have passed closer to Earth than the moon in the span of 2 weeks. The statistical anomaly is confirmed at 4.5 sigma. The multi-domain evidence, atmosphere, lunar surface, cislunar space, converges on a single conclusion. The debris environment in Earth's neighbourhood has changed. We can measure that change. We can document it across multiple independent systems. We can confirm that it is not an artifact of observation or reporting. What we cannot do, not yet, is explain why it happened, what triggered it, or how long it will last. The moon is still getting hit. The fireballs have not stopped, The asteroids keep coming, and the models that were supposed to predict when this would end have been wrong every time. I want to leave you with a thought. Not an answer, because the data does not support one yet, but a thought. For most of human history, we have looked at the sky and assumed it was stable. The same stars, the same planets, the same predictable patterns repeating on schedules we could calculate to the second. And for the most part, that assumption has served us well. The solar system is, on human timescales, a remarkably predictable place. The orbits are stable. The debris environment fluctuates within known bounds. The meteor showers arrive on schedule and depart on schedule. The background hum of small objects entering the atmosphere is steady enough to be boring. But stable on human timescales is not the same as stable. The solar system is a dynamic gravitational environment where everything affects everything else, where small perturbations accumulate over long timescales, and where changes that are invisible for millennia can become suddenly and dramatically apparent when a threshold is crossed. We have been living in a period of relative calm, and we have mistaken that calm for permanence. What the evidence of the past 4 weeks suggests, not proves but suggests, is that the calm may have shifted. Not catastrophically, not apocalyptically. Nothing in the data points to an imminent civilization-threatening impact. But the background level of activity in our immediate neighbourhood appears to have increased, and the cause of that increase is not understood. We are seeing things we did not expect in quantities we cannot explain, from directions that do not match our models. We are not watching random events. We are watching a system change in real time. And until we understand why, the only honest posture is the one the data demands. Eyes open, instruments running, assumptions suspended. The sky is not falling. But something up there has moved, and it has not settled yet.